Let's take a moment to review the canonical unit vectors I, j, and k. These are the vectors that point in the directions of the positive x, y, and z axes. We can express any three-dimensional vector as a linear combination of these unit vectors. In fact, it's essentially what we're doing when we use this notation. We just make it more explicit here by using the letters I, j, and k explicitly. These coefficients of I, j, and k are the components of u in the directions of I, j, and k. But as we've seen in the context of the scalar product, we have a good reason to talk about the component of u in the direction of another arbitrary vector, not just one in the direction of one of the axes. For example, when we looked at work, we saw this picture, where work is the product of the magnitudes of w and v, and the magnitude of w is the component of u in the direction of v. This leads us to the following definition. Consider the vectors u and v and an angle theta between them. The component of u in the direction of v, or the component of u along v, denoted by comp sub v of u, is the magnitude of u times cosine of theta. We can think of this as a signed magnitude, since if theta is between 0 and pi over 2, then the component is positive, and if theta is between pi over 2 and pi, then the component is negative. We can rewrite this by multiplying it by the magnitude of v over itself, at which point we recognize the numerator as the scalar product. We can therefore write the component as the scalar product of u and v over the magnitude of v, which doesn't require that we know theta directly. We can also get a nice formula for w itself in a similar way. We'll do this by specifying a magnitude and a direction for w. It points either in the direction of v or in the opposite direction, so we can start with a unit vector in the direction of v, namely v over its magnitude. We can multiply this by w's signed magnitude that we just saw to get our expression for w. We can also write this as a scalar multiplied by v if we want. We define this as the projection of u onto v. Compare this to u sub 1 times I, which is the projection of u onto the x-axis. The pattern is the same in that we have a signed magnitude times a unit vector in the direction we want. Note that by definition, the magnitude of the projection is the absolute value of the component of u along v.